the importance of the embedded minimal hypersurface of the round sphere also comes from the minimum force in the space. And please try to get any questions. So also one important feature is that the lower bound of area of minimal hypersurfaces directly corresponds to the lower bound of density of minimal. Also the one important result of Simon's classical result of Simon's is that there is no unstable minimal hyperchrome with an isolated similarity. Where the dimension is smaller than equal to. But I want to note that as well here is that the stability of hypercone does not correspond to the stability of minimal hypersurfaces. So for the simple example here, so the crater in S2 is a versus S1, but the flat plane is unstable. So it does not correspond to each other. So any questions support? So there are lots of examples of the minimal hypersurfaces or minimal surfaces. Whose dimension is 1. So I will go over some examples which are so far. So let's start with dimension 3 because if we consider the dimension 2, then we know that the embedded the minimal hypersurface, so embedded close embedded geodesic is only about 2 sphere. So we start with the crater S2 and S3, which is one trivial example, and we know the critical force. So for the critical force, we can write down this by the product of the order of square root of 2 on S1. And so we know that the nucleus, which is so-called loss of temperature, is proven by Brando in 2012, and the Wilmer conjecture, which is proven by Marcus and Davis. So which gives the lower bound of the areas which has a the interior genus of the minimum surface which has a interior genus. So there are two very important results from the critical force. So if we go further over the topology of the minimal surfaces, then the Wilson surface is the minimal surface examples of the minimal surfaces with multiple dimensions. So I'll write down this as a and this gives a genus part. So topology part, and this gives the number of sheets. So this is constructed by the equivariant problem in S3. Yeah. These examples are all S3. Any also, there are constructions by Turing by Turing problem and the culture income. And also there are constructions by the gluing constructions like the which is called the linear gluing method, which has been done by outlets and outlets, yeah. And on view and outlets vectors. And more works. And there are index constructions, which is done by October. And I would write this as a covariant index construction. And the isometry here is a finite. And I would write this as a n or the diagonal dn, etc. So also there are percent constructions, which I should note here is that by eigenvalue imagine. So which gives the variable surfaces in S3, which is a arbitrary genus, and also on S3, and also if one goes to the boundary setting, which is a three-dimensional pool, then they also constructed the pre-boundary minimal surfaces with arbitrary genus, arbitrary number of components. So which is done by Arbutin. Vectors. So at least there are many examples of the minimal surfaces on S3, but we do not know many examples in the higher dimension.
Are they all embedded?
Oh yes.
All of them embedded?
Yes. Yeah, all examples here are all the close to embedded minimal surfaces. So there are examples of hypersurfaces. So we can consider the crater again and the Clifford type hypersurfaces. Also, in higher dimension, actually so we have more kind of way to construct the minimal hypersurfaces, but the less examples are low. So there are methods, which is also really classical. Is that so? We can consider the symmetry. So isometry in this plus one. So let's call this as a homogeneous one construction. So the idea is that, so for instance, if we have Sn plus 1, then consider the isometry of S1 minus 1 plus S02. Then the Sn plus 1 over S1 minus 1 plus S02, which is a orbit space. And also we need to consider this weight metric, and we can consider the geodesic, the two-dimensional domain. So the example of, there are many constructions over this method is that by the Turkey Shen and Shen Wilson. And recently, Carlotto and variations. So the main idea is that, so if you look at this example, then the Ruby space looks like the part of the sphere, and there should be some weight on the metric. And if you want to take a look at the boundary here, then this actually the metric on the boundary here is degenerated to zero. So we can consider this a geodesic, and actually the crater corresponds to this kind of crater. So let's write this by S. And to construct the new minimal hypersurface, we can consider this geodesic, which means the boundary also only. So looks like this one. And also, if we consider the segment here, then this is a minimal hypersurface with the singularity at these 2 points. And what Xian constructed here is that he constructed the minimal hypersurfaces converging to this singular minimal hypersurface. So infinite family of the minimal hypersurfaces, which converges to this singular minimal hypersurface, but which is closely and embedded. So the Xian's example actually gives a counterexample of the spherical constant problem. Which is about the uniqueness. So what he really proved is that non-uniqueness of minimal hypersurface sphere as impossible. So this is very important feature of the higher dimensional sphere. Which may have lots of really linear boundary. So I would draw this kind of example. It's like on the Gaussian space, it should wiggle here and like wiggle again to this kind of minimal hypersurface, which converges to this singular minimal hypersurface. And this is the family of the minimal hypersurface, close embedded. And the another interesting thing is that here the topologies, this is a topology on n sphere, but we have the more segments of this minimal hypersurfaces diverges. So this is kind of example which gives that the more segments is not controlled by this topology.
So those geodesics are all embedded or not embedded?
All embedded. Here is all these examples are embedded, I mentioned.
So how do you prove that it's embedded?
So I can't remember the full detail, but using the degeneracy of the metric on the boundary, and I think one can use the intermediate by Bayes' theorem and counting the number of the intersection number, and one can do that. There is an example, because here the metric is very singular, and really construct there should be some solution of the geodesic equation, which has an arbitrary large number of intersections.
So Carlotto Schulz example, can you explain about that example?
For that, I think I forgot. Yeah. Very well. Yeah. Also, they consider some Ruby space, and I think that they kind of, I'm not sure they used the same Ruby space, but I think so I read that, and what I remember is I think they refined the analytical method, which is available, and I think they so actually what they constructed is that the infinite value of 3-dimensional torus, minimal 3-dimensional Any other questions so far?
So there are infinitely invalid three torus against 4.
Yes.
Minimum.
Minimum. Yeah, I think for the classical constructions rely on the intermediate values theorem, and which proves that there exists this solution which is a Dodge intersection numbers by. So, but what they needed was like more analytic. They needed to bound some terms that they found because their work is much more extensive than the classical works. So there are examples as well. The isoparametric construction. So the isoparametric minimal hypersurface means that the constant principal curvatures. So fix that the minimal hypersurface as a constant principal curvature, and they constructed the isoparametric minimal hypersurface S4. And so this is remarkable because they constructed the minimal hypersurface with conclusion of S3 over T. So the examples here have a minimal hypersurface, the topology of the S3, this three-dimensional sphere, or S2 cross S1 or S1 cross S2, but they constructed new minimal hypersurface with a different topology. More examples. And recently there is a doubling approach by Calculus and Giavaggio. They constructed the infinitely many. So this is right for the slides. Yes, family of minimal hypersurfaces on S4. This first value number goes to infinity. So the first value number here is that the rank of the convolution. And what the method they constructed is that so they have two S3. So they doubled S3 S4. And they doubled two S3 three pairs along S1 plus S1, which is a Clifford plus. Should be S3. Also, there should be a scale, but so they have a lattice over here, so they needed to double along the lattice of the hypercross, and what they constructed is the n² minus 1 connected some of the surfaces. So this is a new minimal hypersurface.
Sorry, could you explain doubling in Korean? Simply, possibly, intuitively?
사실 저도 전문 교수가 아니라서 잘 모르기는 하는데요. S3가 S3가 있으면 여기 사이에 S2 플러스 S1을 하이퍼텐더리드 S2 플러스 I를 넣어서 이제 그 PD를 플러스 이런 이제 미니멀 서비스나 기존의 기준을 넣고 여기 사이에 이제 하이퍼텐더리드 내기 있어요.
내구를 연결한다?
네.
대충 카테는.
네, 그래서 이제 PD를 풀어서 이런 미니멀 서비스가
근데 또 위안에 똑같은 거예요.
근데 시트는 여기서 똑같아요.
그래서 더블링이라고.
더블링은 정확해.
When you generalize that method to three just choose intersecting each other along the equator instead of regional two. If we have three.
Oh, right. So I think it should be 2 and 3. And
Yeah, making the intersecting angle 60 degrees, not 90 degrees.
nothing. 60 degrees or
Like this.
so
Yeah.
this one?
Yeah.
Oh.
Maybe that could be possible, but I'm not sure.
Yeah, so yeah, I did calculate already this paper, so yeah, but yeah, the main idea is like the doubling pairs. And what they use is hypercutting. Yeah, instead of the cutting of the negative distribution.
So do you know that none of these examples are not isoparametric examples? Hopefully not.
For the isoparametric, so I highly doubt that the hypersurface constructed by the method is
sure.
yeah. And but yeah, maybe the trivial example should be isoparametric, and this will be the example potentially. Yeah. And yeah, also the doubling example as well.
So what about the distant example, Cantor example? So it's not.
This one.
Yeah.
Oh yeah. So for this one, yeah, I also doubt it because it also resembles more like a doubling. So the min-max method give another method to kind of double, but the difference is that like for the doubling, the PDE they use the annotating method, but for the min-max it's more geometry. So any other questions from? So now I'll give some based on the method of the so these are the examples in my hypersurface, and I will give some introduction of the max theory. So there are recent development of the max theory in the unbranched side, which gave infinitely many minimal hypersurfaces and then manifold in region 3 to 7. And so which is by purpose. Also prove the minimal conjecture and unconsole and Sinjaro. Yeah, really works on this. And so in the unpurpose setting,